let's look at page 401 in your textbook called 6.3 Modeling Data with Line of Best Fit. As we usually do, we're going to flip to the end of the page or the end of the section on page 407, and you're going to copy that into your learning journal. Okay, so some key terms you need to know. A scatter plot is useful for looking at trends in data. So we're going to create scatter plots on your graphic calculator. And if the points on a scatter plot seem to follow a linear trend, then there may be a linear relationship between the independent and dependent variable. And we'll look at that when we look at examples. So things you need to know. If the points on a scatter plot follow a linear trend, technology can be used to determine the graph of the equation of line of best fit. Technology using linear regression to determine the line of best fit. Linear regression results in an equation that balances the points of the scatter plot. The line of best fit can be used to predict values that are not recorded on the plot. Okay, so for example, you'll get a bunch of data, you'll type it into the graphing calculator using the stats function like you've done before, and you'll hit linear regression instead of sine regression, and the calculator will tell you your equation for the line. You can then use this equation for the line to interpolate your data and extrapolate your data. So let's flip back into your book to see what line of best fit and regression actually are for definitions. All right, so line of best fit is a straight line that best approximates the trend on your scatter plot, and a regression function is a line or curve of best fit developed through a statistical analysis of data, which produces you an equation you can use to solve other problems. So page 402 on your textbook gives you example number 1. So we're going to use technology to determine a linear model for continuous data. So the 1 hour record is the farthest distance traveled by a bicycle in 1 hour. The table below shows the world record distances and the data and the dates they were accomplished. So how are you going to actually put this in your graphing calculator? So use technology to create a scatter plot and determine the equation of the line of best fit. So you're going to go to your calculator, and hopefully mine's working. Yay! So I'm going to go into the stat function, and I'm going to go to edit my list, and I'm going to go clear these lists. So if you go to the top of L2, and if you hit clear and then down, it'll clear the entire column for you. So clear and down, and now we can enter our data. So how are we going to enter our numbers for years? What we did before is we just put a 1, 2, etc. So the year starts at 1996, and then it goes to 98, 99, 2002, 2004, 2007, 2009, etc. So we could put the years in, right? So the first year is 1996, hit enter. I'm just going to pause, I'll enter all the data so you don't have to watch that part of the video. So once you have all your data, just double check it to make sure it's correct. So the date or time is always in L1, and your dependent variable is always in L2. So you're going to go back to stat, just like we did with the sine regression. You're going to go over to calculate, and you're going to look for something that says linear regression or LIN reg. You're going to hit enter, and then you're going to hit enter again. Your calculator is going to look a little different. Just hit calculate, and the calculator's thinking, and it actually gives you the equation. So the equation of the line reads y equals 0.85 or 86, but since we're in applied and we want to keep as many decimals as possible till your final answer, let's keep at least 4 decimals. So it'd be y equals 0.8585 x plus b, but b is negative, so it'll be minus 1635.73. Maybe let's keep 2, so 3. Okay, and that's your actual equation for the line of data that you fit, so that's question A. Okay, so I'm just going to write the equation on the question here so you can see it. So y equals the 0.8585 x minus 1635.73. interpolate. And interpolate means to estimate a value within the domain of the set of data that you're given. So we're going to interpolate that the distance for the year 2006. So we're going to go back to our graphing calculator with our linear regression. Now we're going to have to put our equation into our graph. So we go back to the y equals, clear any previous data you had, and I'm going to type in my 0.8585x. And I'm going to subtract my 1635.73. And if I go to graph it, it won't graph because I have to change my windows. Because my x values started in 1996 and they ended in 2009. So I want large x numbers, right? So my x minimum, I could just put 1995 maybe. And then my x maximum could be up to 2010. Each scale number could be 1. My my minimum data for the distance was roughly about 78, and my maximum for that data was roughly about 90. So let's make it about 91. My scale, I guess I could put 2, and I'm getting an error down here saying check values in window, x min is greater than x max. Oh, it fixed itself, and I get a line. Okay, so I go to my graph, I look, I have a linear regression. It's an increasing regression, so it's showing that as the years go on, the data is increasing. Now I go to second function, trace, and I want the value, so I hit enter on the 1, and I want the value at 2006. So 2006, type it in, if I hit enter, it'll give me the corresponding y. So the interpolation, so a possible world record distance for the year in 2006 was 86.42 kilometers. So that's my answer for B. I'm just going to switch back and write it on there. So the window's open. Okay. So that answer was 86.42 kilometers. And C says, compare your estimate with the actual world record distance of 85.99 kilometers. Okay, so if you subtract 86.42 minus 85.99, I get a 0.43 difference in my data. So it's roughly, if you look at it, it's less than half a kilometer. Okay, let's look at example number 2 now. Okay, example number 2. So Matt buys t-shirts for a company that prints art on t-shirts and then resells them. When buying the t-shirts, the price Matt must pay is related to the size of the order. So it's like you buy more, you get a better deal, right? 5 of Matt's past orders are listed on the table below. So if he bought 500 shirts, he paid $3.25 per shirt, versus if he bought 740 shirts, he paid $1.69. Okay? Matt has misplaced the information from his supplier about the price discounts on bulk orders. He would like to get the price per shirt below $1.50 on his next order. I use technology to create a scatter plot to determine the equation for the linear regression. So you want to extrapolate the data. Means that you're going to pick a data point on the range that's outside of the data values given. So you're going to extend the graph is really what extrapolation means. Okay, so first of all, we're going to go to our graphing calculator, and we're going to go back into stat, and we're going to go back into edit, and we're going to make a new list of data using the data in the textbook. So just make sure you clear your data table, your list beforehand so you don't get any error, and then you just start typing. So the first number is 500, second is 700, and so on and so forth. I'm just going to pause so I can type it in, and then you don't have to watch that part. So I have my data entered. I just double check it quickly. I go back into stat to get my linear regression, and the calculator stopped working. It's thinking. Okay, it looks like my calculator doesn't want to work, so I'll just give you the answer. So if you enter your stat and then you go to linear regression again like we did in the first example, you'll see that the equation for this data is y equals negative 0.0065x plus 6.5. Okay, so what does the slope and the y-intercept of the equation of the linear regression represent in this example? Okay, so if you remember y is equal to mx plus b, m is always your slope. So your slope is equal to negative 0.0065. What does that actually tell you? It tells you since it's negative, the graph is descending, so you're actually getting a drop in price, which you can see from the data table anyways. Okay? If I look at the y-intercept, it's always the second part of the equation, and that is your 6.5. So y-int is equal to 6.5. Okay? So C says, use the linear regression function to extrapolate the size of the order necessary to achieve the price of $1.50 per shirt. So I don't know if I can write on this part. So I'm just going to go to here to write. Okay, so C. Okay, so if I take my original equation of y equals negative 0.0065x plus 6.5, I want to figure out the price or how many t-shirts Matt needs to order if the price of the t-shirt is $1.50. Is the price of the t-shirt your x variable or your y variable? You have to remember that the number of t-shirts was your independent, and it was based on, or his order was based on how many shirts he ordered as to the price. So y is going to be your independent or dependent. So you're going to make 150 is equal to y is negative 0.0065x plus 6.5. Now you're just going to use simple algebra to solve this equation. So first of all, we want to move 6.5 over to this side. So it'll be 1.50 minus 6.5 is equal to negative 0.0065x. And we want to get x alone. X is multiplied by your slope. So the opposite of multiplication is division. So if you divide both sides by 0.065, you should get your answer. These cross out. And you get an answer of about 769.2 is equal to x. You can't buy 0.2 of a t-shirt, so you're going to have to round up. So he should buy 770 t-shirts because he wants to pay $1.50 per t-shirt. And that's your answer. Now your questions that you're going to do or attempt are on page 407, question 3, 6, 7, 9, and 11. Now the next units that we're going to be looking at is the same idea. So it's just going to be using a different linear regression, but it's the same idea. You're going to enter data into a table, and then you're going to choose a linear regression that best suits it, and then you're going to answer questions based on the equation you're given.